So we're going to do more Green's theorem today. So I want to start with an example that kind of leads into what we're going to talk about today. So we want to find the work done by F our force is e to the x minus 3yi plus e to the x plus 6, or e to the y plus 6yj. We want to find the work done by this force moving a particle around the curve r equals 2 cosine theta. And we're going counterclockwise. So our work is the line integral of the force around the curve. So we're looking for the line integral of f dot dr. And we're going to use Green's theorem to evaluate our line integral. So in this case, our m is e to the x minus 3y, and n equals e to the y plus 6, and I think this should be an x, 6x, yes, plus 6x. So dm dy is minus 3, and dn dx is 6. So our field is not conservative, so our line integral is not 0. But what we end up with is dn dx minus dm dy, which is what we need to use Green's theorem, is 9. So using Green's theorem, we need to evaluate the integral over our region of 9 dA. And that equals 9 times the double integral over our region of dA. So the double integral over our region of dA is what? That's just the area of the region. So this is just 9 times area of region. Does anybody remember what the graph of r equals 2 cosine theta is? So this is not y equals cosine x, r equals 2 cosine theta. So we're in polar coordinates, right? So it's a circle. I'll just sketch it out really quick. Our circle looks like so. And we're going counterclockwise. And this is x equals 2. So this is a circle of radius 1. So our integral turns out to be 9 pi. So our line integral, in this case, using Green's theorem, turned into just finding the area of the region. We did an example like that yesterday, where when we applied Green's theorem, dn dx minus dm dy turned out to be 1, and we found our line integral reduced to finding the area of the region again. So this leads us into one application of Green's theorem. If we can find n and m so that dn dx minus dm dy is a constant, and it would be especially nice if that constant was 1, then applying Green's theorem in reverse, essentially, lets us find the area of a region by evaluating a line integral. So depending on the region, it might be easier to evaluate the line integral than to evaluate this double integral. So that's kind of the point of what we're doing today. We want to find area using Green's theorem. So what we saw in our last problem is if dn dx minus dm dy equals 1, then using Green's theorem, we end up with just the double integral over our region of r dA. So if we're trying to find our area, we want to pick n and m so that dn dx minus dm dy equals 1. So what we do, our little trick here, is we let m equals minus y over 2. And let n equal x over 2. If we pick this as m and n, if we're trying to find our area, we pick m and n like this, then dn dx minus dm dy will always equal 1. And we apply Green's theorem in reverse. So we're going to state that as a, I don't know, not exactly a theorem, but just as a result. So we're going to say we'll say it kind of formally, the area of a region R bounded by a piecewise smooth, simple closed curve. So it satisfies the conditions of Green's theorem. And we'll say curve C is given by our area equals 1/2 the integral of minus y dx plus x dy. So this, if we pick our m and n, so that m is minus y and n is x, then when we take our partials to apply Green's theorem, we end up, actually in this case we end up with dn dx minus dn dy is 2. That's why we end up with this dividing by 1/2. If we pick our m and n this way, then we can find the area of a region by evaluating, and this should be C, by evaluating this, and I'll put my little circle here because it's a closed curve, by evaluating this line integral. And often, if you have a complicated region, it's much easier to evaluate this line integral than it is to evaluate the double integral over the region. So this is just another application of Green's theorem. So any questions on the setup, how we set this up? All right, I just want to look at one quick example, and then I want to go into do a couple of derivations to give us some motivation for what we're doing for the end of the unit. All right, so our example. We want to use a line integral. We want to find the area enclosed so our curve is given by parametric equations. So R equals t squared I plus t cubed over 3 minus tj. For t negative square root of 3 less than or equal to t less than or equal to square root of 3. So we want to find this area. If we were to graph this, if you graph this in your calculator, our graph, I'm going to sketch a quick graph here just so we can visualize what we're talking about. The graph of this thing looks something like that. And we're going around the curve this way. And on negative square root of 3 to square root of 3, it makes one loop. So, we're looking for where y is 0, so where this component is 0, and this component is 0 at negative square root of 3 and square root of 3. So it's kind of like a polar graph where it turns out to be, it repeats on that interval. So if we were to try to find the area using a double integral, we would have to, on this integral, we would have to figure out that x, we could say x varies from 0 to square root of 3, but y varies between here and here. So this could be a really complicated double integral to evaluate. We're going to use a line integral. We're going to use Green's theorem in reverse. So we want the double integral over the region of dA. And we know that the double integral over our R of dA from Green's theorem equals 1/2 the integral on our closed curve of minus y dx plus x dy. So on our curve, x equals t squared. So dx equals 2t dt. And y equals t cubed over 3 minus t. So dy is t squared minus 1. Dt. So we're going to substitute these in to this line integral and evaluate this line integral. So our area is 1/2 the integral from negative square root of 3 to square root of 3 of negative y dx, so minus t cubed over 3 minus t, and dx is 2t dt, plus x dy, so x is t squared, and dy is t squared minus 1 dt. So we're just now we're evaluating this line integral. We can simplify this. This turns into evaluating an integral with just polynomials. We end up just using an integral with polynomials. So this is an easy integral to evaluate. It takes a little bit of simplification, but we just end up with powers of t that we're integrating. When we evaluate this, we end up with 1/15, 3 to the 5 halves, which is approximately 1.039. So we turn that complicated double integral into a relatively easy single integral using Green's theorem. Questions on that? So when a problem asks you to use a line integral to find the area, they're asking you to apply this form of Green's theorem. All right? Okay. Now what I really wanted to do today. This is good. This is nice, a nice application of Green's theorem. But what I want to get into is using Green's theorem as a preview for what we're going to talk about at the end of the chapter, the other two big results that we're going to get to in this chapter. So we're going to talk about a couple of alternate forms of Green's theorem. And remember that Green's theorem applies in the plane. We're going to do these derivations in the plane. What we're going to do at the end of the unit is extend these into space. But this gives us a nice introduction because we have all the tools to do this now. So we're going to let our vector field equal mi plus nj plus 0k. So our field is in the plane. I'm just adding this k component because we're going to be doing something with the cross product. So our field is in the plane. We're going to calculate the curl of f. We talked about the curl at the beginning of the chapter, and we really haven't done much with it yet. So this gives us an idea of how we might apply this. So the curl of f is this determinant and when we find this determinant, we get it's minus dn dz I plus dm dz j plus this quantity dn dx minus dm dy k. So do we recognize any of these quantities? This one is what we use in Green's theorem, right? So we're going to now take the dot product of our curl, del cross f. We're going to dot that with k. That'll isolate this component. So del cross f dot k is just this quantity. And using this, so now we can write, because this is part of Green's theorem, we can write that the integral the line integral along a curve of m dx plus n dy, our line integral of our vector field, equals, and that's the same, I'm just going to make this notation as a reminder, this is f dot dr. This equals the double integral over our region of del cross f dot k dA. So what we're saying here, we're extending Green's theorem into 3 dimensions, and when we extend this to 3 dimensions, this is called Stokes theorem. This is one of our big results that we're going to get to at the end of the unit. But it says that the line integral of the tangential component of f, that's what the line integral tells us. We're summing the component of f that's in the direction of our path around the curve is equal to the double integral of the vertical component of the curl. So what this is saying is, if we have a vector field, and remember the right-hand rule, so our curl points in the direction of our thumb. So we're looking at the vertical component of the curl. If the curl has a large vertical component, then the sum of our tangential components of f around the boundary is also going to be large. So this says something about the curl producing a rotation in our region. If our curl has a large vertical component, so we think about our right-hand rule, that means the component that points in the direction of our thumb is large. That means that the tangential components around our fingers is also large. So the curl, this tells us something about the relationship between the curl and a rotation. And we'll extend this to 3 dimensions later in the chapter. So this is the first kind of preview of what we're going to talk about. So again, the tangential component of f around the boundary of our curve is equal to the double integral of the normal component over the region enclosed by the curve. All right, now we're going to look at the normal component. So this is a tangential. We talked about the tangential component of f. Now we're going to do something similar for the normal component of f. So the line integral tells us something about the tangential component. Now we're going to work with the normal component. So let's let our path be given by this vector function. So our path is x of t I plus y of t j plus, and we're in the plane, so we don't have a z component, for a less than or equal to t less than or equal to b. So this is our path. Our tangential component, our unit tangent vector, if we remember back to the beginning of the unit, r prime over the length of r prime, or not the unit of the year. R prime over the length of r prime, if we're using this for r, is x prime over the length of r prime, I, plus y prime over the length of r prime j. And we want to look at, so this is our unit tangent vector. We want to look at the unit normal vector. So the unit normal vector, and we're interested in the outward unit normal vector. And I'm just going to use a small n for our unit normal vector. In the plane, to find our unit normal vector, we can switch x and y and change the sign on one of them. So we're going to write this as y prime over the length of r prime minus x prime over the length of r prime. And this is I and j. And the reason we picked this, the reason I changed the signs this way is if we have a curve in the xy plane, like so, and our unit tangent vector is here, and we're trying, our positive orientation is counterclockwise, our unit normal vector is here. So we want our inward pointing unit normal vector here would switch the coordinates on the x. We want the y coordinates to stay the same. Then that keeps our unit normal vector pointing outward. If we switched the sign on the y, that would point our unit normal vector inward. So if we had a plus x and a minus y, our unit normal vector would point inward. So that's why we picked this particular version of the unit normal vector. All right, so here's our expression for the unit normal vector. And we let our field, our force, if we're thinking of a force, our F is mi plus nj, just like we've been using all chapter. So we're going to use a line integral to sum the normal components of F. So we want to sum the normal components of F. So we're looking at the line integral around our curve of f dot n ds. F dot n is going to give us the normal component of F, the component of F in the direction of n. So we're looking at this line integral, and we're going to use what we have here to express this dot product. This is equal to the integral from a to b, and this is a scalar line integral because f dot n is a scalar. So this is mi plus nj, and we're taking the dot product with our outward unit normal vector. So there's our expression for our line integral. And when we take our dot product here, so this equals the integral from a to b. When we do our dot product, we get m y prime over the length of r prime minus n x prime over the length of r prime.
Is m a vector?
M is just a scalar function.
So when you have the vector sign.
Oh, sorry. Thank you. So this is our dot product times ds. So this is our line integral. And remember that ds equals the length of r prime times dt if we parameterize our curve in terms of time. So our line integral turns into, when we substitute this for ds, integral of a to b of m, and I'm going to write this in d notation, dy dt, minus n dx dt, my r primes cancel, times dt. And this is equal to, finally, we're getting to our result, equal to the line integral around a curve of minus n dx plus m dy. And now we're going to apply Green's theorem to this line integral. So this finally equals the double integral over our region of dm dx plus dn dy dA. So we're applying Green's theorem to this line integral, and I'm just going to say by Green's theorem. But what is this quantity dm dx plus dn dy? Does anybody recognize this? Let's go up here and look. F, so this f is mi plus nj, and we're adding the partial derivative of the x component with respect to x plus the partial derivative of the y component with respect to y. Divergence. This is the divergence of f. This equals the double integral over our region of del dot f dA, because dm dx plus dn dy equals del dot f. So what this tells us, finally, let's go back up to what we started with. The line integral of the normal component of our field around the curve. The line integral of the normal component of our field around the curve equals the double integral of the divergence of the field over the region. So what this is telling us is that if we sum the normal components on the boundary of our region, that is equal to the divergence of the field inside the region. The divergence is telling us something about the field flowing outward. So we're summing the normal components of our field on the boundary. That's the same as the divergence of the field over the region. So the divergence is telling us something about the field flowing outward from our region. And we'll extend this to 3 dimensions a little later, and this will be called the divergence theorem. And I'm just going to rewrite what we started with. This is f dot n ds, and that equals the divergence of f. And one of the reasons that we're doing this is because the divergence over divergence over a region is something that we're interested in physics. We call it the flux. So that talks about the flux of a field. And the curl you're interested in physics, in fluid dynamics and aerodynamics, has to do with the rotation of the field. So we're summing those two things over over a region. And both of these again are extensions of the fundamental theorem, because we're talking about a quantity on the interior of a region being related to that quantity, something to do with that quantity on the boundary of the region. So this relates something on the interior of the region to evaluating something on the boundary of the region. So these are kind of generalizations and extensions of the fundamental theorem. Questions? All right. Homework. There you go.